When we use the term significant, a lot of times we often think of that word as meaning important. And significant figures or significant digits in chemistry and science are important, but more so what the term significant means is that they are measured digits. So when we look at a measurement and we see a digit there and it's considered a significant digit, it means that whatever instrument we used was capable of measuring to that particular decimal place. How many digits we can use is directly dependent on the instrument itself. For instance, the more markings that an instrument has, generally the greater the number of decimal places that you can report with that. Whenever you're making your measurements, you always want to read to the smallest division that's allowed by that instrument. And then once you've read to that last line, there's always the possibility that it's going to extend past that mark, and it's going to be in between marks on the instruments. And so for that reason, we always estimate to the nearest tenth of the smallest marking. So your object, or whether you're talking about the meniscus on a liquid volume, you read to the last mark that it surpasses and accurately interpret what that mark is, and then you estimate one additional decimal place. You go one place past it. But that's all the further you can go. Just one. Can't add any more decimal places beyond that. Now, in terms of looking at a measurement and determining how many significant figures there are, this is going to be important because when it comes time to do calculations with these measurements, we need to be able to identify how many digits are significant and how many are not. The first rule applies to 90% of the possible digits you might have, and that is 1 through 9. All non-zero digits are always considered to be significant, so there's never any question about them. The only ones that there's questions about, or the only one that there's a question about, is the digit 0. And so with zeros, it depends upon where the 0 is placed and also a decimal point. Is there a decimal point visible or not? Anytime you have a 0 that's in between two non-zero digits, kind of like a sandwich, those zeros are automatically significant. You don't have to question those. And it doesn't have to be, a non-zero digit immediately to the left or the right. As long as it's in between two non-zeros, no matter how close or far away the non-zero digits are, sandwich zeros are always significant. If we talk about trailing zeros, now these would be zeros that are towards the right-hand side of the number. They're at the end of the number. Trailing zeros, you have to see if there is a visible decimal point shown in the number. If there is literally a decimal point shown, then zeros that are at the end of the number, no matter where they are in relation to the decimal point, left or right, trailing zeros with a visible decimal point are considered significant, should be counted. However, if there is no visible decimal point, if we just kind of understand, oh yeah, that's where the decimal point is supposed to be, and there's trailing zeros, those zeros are not significant. They are placeholders. They are simply there to hold the significant digits in the proper decimal place so that we understand the correct magnitude of the number. The final kind of zero we consider are leading zeros. These would be zeros at the front of the number, where we typically don't expect to write zeros, but a lot of times we see these with numbers less than 1 or very small decimal values. Sometimes you'll see a 0 written in front of a decimal point, and a lot of times that's simply so that we don't accidentally lose the decimal point if we're writing it and we're in a hurry. It might just look like a speck on the paper. But leading zeros, no matter the case, no matter how many there are, they are never significant. Their sole purpose is either to, as I said, make sure we don't lose the decimal point, the very front 0, or to hold open the tenths, the hundredths, the thousandths, however many decimal places we need until we get to the non-zero digit that's expressing that fraction of 1. If we take a look at some example measurements, we can determine how many significant figures there are in each measurement, and this is going to play into our calculations if and when we were to use these in a calculation. So in looking at the first example, you can see that we have 32.5 centimeters, and the first rule with significant digits is that all non-zero digits, no matter where they're at decimal place wise, are always significant. So the 3 the 2, and the 5 are all going to be significant, and therefore we would have 3 sig figs. And we'll use SF as our abbreviation for sig figs. In the next example here, we have 0.050 grams. Now the 5, we know, is a non-zero digit, so that's automatically going to be significant. But now we've got these zeros, both at the front and also at the back, that we need to worry about. In terms of trailing zeros, which is what this 0 right here would be an example of. Okay? Trailing zeros are going to be significant if there is a visible decimal point. And since we have a visible decimal point in the number, okay, this 0 that is to the right, that is trailing, is considered significant. Okay? The zeros that are in front of the 5 are what we call leading zeros, and leading zeros are never significant. The only reason that they're there, okay, is to help us to keep the correct decimal place, but also help us from losing that decimal point. So this 0 is there simply so that we don't lose that decimal point. This 0 is here so that we make sure that the 5 is in the proper decimal notation, in the proper decimal place, the hundredths place. So in this case, we would have 2 significant figures. In the next number, 2,005 milliliters, the 2 and the 5 are automatically significant because of their non-zero status. But the zeros that are in between, anytime you have zeros between non-zero digits, we call them sandwich zeros. Sandwich zeros are always significant. So 2,005 milliliters would have a total of 4 sig figs. The next 2 examples here look very similar, but there's an important difference. And the difference lies in that visible decimal point. So the 1 and the 6 we know are going to be significant in both of these. And we would read them both as 1,600 kilometers, but the difference is in the precision of the measurement. Because that decimal point is visible, these 2 zeros, these trailing zeros, all right, have a visible decimal point, therefore they are considered significant. And so we would have 4 sig figs in this measurement. In the next 1,600 kilometers, however, there is no expressed decimal point. It's understood to be there, but it is not physically written in. And so what that is telling us is that this measurement of 1,600 kilometers is only known with certainty to the nearest 100 kilometers. And those 2 zeros are simply placeholders to hold the 1's and the 10's place open so that the 6 can express 600 and the 1 can express 1,000. So this measurement has only 2 significant figures. And so you can see that the difference in your precision is communicated based solely on that visible decimal point. So you do need to pay attention, should I be putting a decimal point in or not. The last example here, 0.800 grams. Again, we have 2 trailing zeros. We have our 8, which is automatically significant. 2 trailing zeros with an expressed decimal, so they are both going to be significant. This leading zeros are never going to be significant. So 0.800 grams gives us 3 sig figs. You may say, why do we need to include those zeros at the end? If I put it in the calculator, it's still going to evaluate as if I just put in 8/10. But when it comes to rounding your answers off for any calculation that you use the 0.800 grams in, this is telling us that we know the precision of this mass not to the nearest tenth of a gram, not to the nearest hundredth of a gram, but to the nearest thousandth of a gram. And we have 800 thousandths of a gram. When we use measurements that we have made and determine the proper number of significant digits for, we have to be careful how we round our answers off in calculations. And how we're going to round them off depends on the sort of operation we're doing. With multiplication and division, you need to look at the terms that you're using in that multiplication and division and determine how many sig figs are in each. Now, the answer that we need to round off from the calculator is going to be determined based on the fewest number of sig figs in the terms that we're using, because the fewer the sig figs, the less precise the value is, and therefore that's going to play into how much precision we can report in our calculated answer. So when you multiply and divide, you count the number of sig figs in the terms. Whatever the fewest number is, that's how you round your answer off. When you look at your raw answer out of the calculator or on paper, You start with the left-hand most non-zero digit, so discount any leading zeros, and then for however many sig figs you're to keep, you count from that first decimal place to the right. Now, what exact decimal place is going to be reported in the answer is dependent upon the number of sig figs you can report, not specifically what the decimal place is. That's for multiplication and division. For addition and subtraction, what you need to do is, just like in grade school, you want to line up your decimal points. And you're going to do the addition or subtraction, get a raw answer, but you're going to round your answer off based on the least accurate decimal place. So now this time you're not paying attention to number of sig figs, but rather the number of decimal places, and whichever one goes out the fewest number of decimal places, wherever that last significant digit is, that's where you're going to round your answer off to. The last thing to consider is the type of number. If it's an exact number or a counted number, then you're not going to consider it for sig figs. Right? They're considered to be measurements or numbers that have no uncertainty to them, and therefore we don't need to consider them for significant figure rounding purposes. If we take a look at this example, you can see that of the three terms, the first one is only out to the hundredths place, and so our answer is going to be to the rounded off to the hundredths place as well, simply because we have no idea what the thousandths digit is for that first term. In the subtraction problem here, same deal. We've got the first value going to tenths, the second one goes out to thousandths, but we have no idea what the hundredths or thousandths are in that first term. So in our answer, there's no way we can possibly report the hundredths or thousandths place with any degree of certainty. With multiplication, right, we're going to get our raw answer, but then we're going to round off based on the fewest number of sig figs, which is, we've got 4 for the first one, 3 for the second one, and 4 for the last one. So when we round this off, we're going to round it off, start with the left-hand most digit, count 3 in, and so that's going to take us to the ones place, look to the next digit for rounding, and that's going to round us up to 278.